We defined the Bruhat order on the symmetric group in terms of reduced expressions and subwords of those. And we proved that another alternative definition of the Bruhat order can be formulated in terms of multiplying by transpositions. I want to review those two definitions and show you 4 more equivalent definitions of the Bruhat order. So we defined U to be less than or equal to W if some reduced expression for W contains a reduced expression for U as a subword. A very closely related characterization of the Bruhat order is that U is less than or equal to W if each reduced expression for W contains a reduced expression for U as a subword. So you don't have to worry about if you found the right reduced expression for W, because it turns out that every reduced expression for W will contain a reduced expression for U as a subword if W is indeed greater than or equal to U in the Bruhat order. Now we showed a different characterization that U is less than or equal to W if there exist transpositions T1 through Tm with W equal to Tm, Tm minus 1, etc., T2, T1, U, and the length of Ti through T1 U being greater than the length of Ti minus 1 through T1 U. So every time we multiply by a transposition, we're making the length of the resulting permutation longer than what we had before. And then related to this characterization, we have U is less than or equal to W if length of W equals length of U plus some number P, and there exist transpositions TP through T1 with W being equal to TP through T1 U. And so this is almost the same, except the length every time we multiply by a transposition is going to go up by exactly 1. So length of Ti through T1 U equals 1 plus the length of t I minus 1 through t1 u. So it's possible to pick transpositions so that we go up in length by exactly 1 each time. Now that doesn't necessarily mean that the transpositions are adjacent transpositions, that is generators of the symmetric group. Because if we look at S3, we have 3, 2, 1, 3, 1, 2, 2, 3, 1, 1, 3, 2, 2, 1, 3, 1, 2, 3. If we look at this path from 1, 2, 3 to 3, 2, 1, now here's another path. So 1, 3, 1, 2, 3 equals 3, 2, 1. So there's just one transposition where we go up in length when we apply it, and that actually sends us from 1, 2, 3 all the way up to 3, 2, 1. Or we could take another path going through 2, 1, 3 to 3, 1, 2 to 3, 2, 1. We could say that 3, 2, 1 equals 1, 2, 3. We apply S1, which is a transposition 1, 2. And then from here to there, we apply 1, 3 to switch the letters in positions 1 and 3. And then from here to there, we apply S2, which is the transposition 2, 3. Now, I suppose we could have gone all the way up the left or all the way up the right to use just S's 1, 2, 2, 3, 1, 2, etc. as our reflections, our transpositions. But this result says we don't necessarily need to use the adjacent transpositions. There are transpositions that make the length go up by exactly 1. Here we've got length 0, length 1, length 2, length 3. Alright, so this characterization is very much like that one, except the length goes up by exactly 1 each time. Now I want to show you two characterizations that are rather different. So if we're given a word A1 through AK, I want to put a line on it, and I want to make that the increasing rearrangement of the word. So it turns out that U is less than or equal to W in the Bruhat order. These definitions are all if and only if, really. If and only if U1 through UI is component-wise less than or equal to W1 through WI if we write both words in increasing order. Let me do an example of this. So 2, 3, 1, 4, 6, 5 is less than 2, 6, 1, 4, 3, 5. Actually, this is sort of silly because the only difference between these two permutations is the transposition of the 3 and 6 in positions 2 and 5. So we can see that immediately. But let's use this criterion anyway. So if we look at the one-letter subwords, we have 2 is less than or equal to 2. And then the two-letter subwords, 2, 3, and 2, 6. 2, 3 is less than or equal to 2, 6 component-wise, because 2 is less than or equal to 2 and 3 is less than or equal to 6. Then if we look at the first 3 letters, we've got rewriting them in order 1, 2, 3, and 1, 2, 6. Here, 1 is less than 1, 2 is less than or equal to 2, 3 is less than or equal to 6. And then the first 4 letters, 1, 2, 3, 4, and 1, 2, 4, 6. 1 and 2 are equal to 1 and 2. 3 is less than 4, 4 is less than 6. And then do the first 5 numbers on each side. That's 1, 2, 3, 4, 6, and 1, 2, 3, 4, 6. And then, of course, 1, 2, 3, 4, 5, 6 when we put in all the letters. So we have this prefix rearrangement order. We check the one-letter prefixes, the 2-letter, 3-letter, 4-letter, with the words rearranged into increasing order. And then if one permutation comes out less than or equal to other in all n cases, then that one's less than or equal to the other one in the Bruhat order. Of course, strictly less than in this case because they're not the same permutation. So that's the 5th characterization. A 6th one involves the permutation matrices. So let's let P of W be the permutation matrix. Of W. So that means P of W has entries Pij, where Pij is 1 if J equals Wi and 0 otherwise. And then we define another matrix, Q of W, by letting Qij equal the sum of the entries in the first I rows and the first j columns of P. Or in other words, the number of ones in the I by j submatrix in the upper left I by j submatrix of P. So let's, as an example, consider all 6 permutations in S3. So we've got 1, 2, 3, 3, 2, 1 at the top. 3, 1, 2, 2, 3, 1. 1, 3, 2. 1, 2, 3. 2, 1, 3. And then the permutation matrices are 3, 2, 1, 2, 3, 1, 3, 1, 2, 2, 1, 3, 1, 3, 2, and 1, 2, 3. All right, now for every entry, I'm going to count the number of ones in that position and above it and to the left. So that's going to be 0, 0, 1, 0, 1, 2, because there's 2 ones above and to the left of this position. 1, 2, 3. And we'll always have 1 to n in the last column and 1 to n in the last row, because we've got exactly 1, 1 in every column and in every row. So if we go from left to right in the bottom row, we will have seen a single 1, 2 1s, 3 1s, 4 1s, etc. above it. Same thing with the last column. All right, here we have 0, 1, 1, 0, 1, 2, 1, 2, 3. And then here, 0, 0, 1, 1, 1, 2, 1, 2, 3. Here, 0, 1, 1, 1, 2, 2, 1, 2, 3. 1, 0, 1, 1, 1. 1, 1, 2, and 1, 2, 3. And finally, 1, 1, 1, 1, 2, 2, 1, 2, 3. All right, now the way we compare the matrices is sort of the opposite of what we just did for the prefixes in increasing order. If we look component-wise at the matrices, it's the lowest one in the Bruhat order that actually has components which are greater than or equal to everything else. So it turns out that U is less than or equal to W in the Bruhat order if and only if Q of U is component-wise greater than or equal to Q of W. Maybe it would be interesting to go back to the other example I did. So if we have 2, 3, 1, 4, 6, 5, then the permutation matrix is 1, 0, 1, 4 zeros, 1 in position 3, 1 in position 4, oops, 2, 3, 1. That third row should have a 1 in position 1. And then a 1 in position 4, a 1 in position 6, and a 1 in position 5. Now this becomes 0, 1, 1, 1, 1, 1, 0, 1, 2, and all 2's, 1, 2, 3, and all 3's, 1, 2, 3, and now fourth 1, 1, 2, 3, 4, still only 4 here, and then 5, and then 1, 2, 3, 4, 5, 6. If we do that for the other matrix, 2, 6, 1, 4, 3, 5, then we have a 1 in position 2, a 1 in position 6, 1 in position 1, 4, 3, 5, and then adding up the ones in the submatrices, we have 0, 1, 4 ones, 0, 1, ones all the way till the end when we get 2 ones now in this upper submatrix. 1, 2, and a 3 in this position. 1, 2, 2, 3. And then 3, 4. In row 5 we've got 1, 2, 3, 4, 4, 5. And then in the last row, 1, 2, 3, 4, 5, 6. So the first rows are the same. In the second row, this one is greater than or equal to that one. And then this row is different also. It's greater than or equal to that one because the 3 start earlier. 1, 2, 3, 4, 4, 4 is greater than 1, 2, 2, 3, 3, 4. 1, 2, 3, 4, 4, 5 is the same. 1, 2, 3, 4, 5, 6 is the same. So since these entries are all greater than or equal to those entries, this permutation is less than that permutation in the Bruhat order. The end.